Have you ever wondered if we live inside of a computer simulation? This is actually a theory, you may have heard of it before, but imagine a highly advanced civilization that would like to find the cures to all disease, that would like to solve all the engineering problems of their world. What might they do? They might build a supercomputer that allows them to simulate themselves. Maybe simulate humanity, maybe simulate whatever alien beings they are. And because it's a computer simulation, they can adjust the speed. So imagine setting the rules for life, letting the simulation play out, but watching it play out at like 1 million times normal speed. Then they can just check in on the simulation in, say, like 5 minutes, which would have been like 20 billion years, and then check and see what the simulation came up with to solve all the problems of the world. They would have already discovered all the cool technologies. They would have already solved all of the cool medical problems. Well, not cool medical problems, but you know what I mean. It's a pretty out there theory, but if you think about it, all you would really need to do is simulate physics at the lowest possible level. If you could simulate the interaction of atoms, the positive attracting a negative, and all of those sort of logics of the very fundamental chemistry, then theoretically that should manifest into the rich world that we have today. And in fact, although this theory sounds far-fetched, and I'm not at all trying to speculate on the nature of our universe, we are actually doing this on a smaller scale already. And of course, I'm referring to molecular modeling. So it turns out that pharmaceutical companies have successfully looked at enzyme active sites, say for like a breast cancer cell. They would look at some active sites of this breast cancer cell, and they would test different molecules in the active site to see if any of these molecules fit inside of that slot. And the idea is that if you find a molecule that fits inside of an enzyme slot, it can deactivate that enzyme, and that could act as a cancer drug. And this has been successfully applied many, many, many times. So here you can see these little helices, these coils, representing a protein. And this molecule here in the middle represents a drug. So in a way, we are using computer simulations just on a very, very small scale. You can see that we don't have the computational power to fully simulate the molecular structure of the proteins, but rather we use a simplified sort of helix to do that. And we have successfully created life-saving drugs using that technology. So all we would really need to do is maybe like grow this idea out and have more computational power and be able to, instead of making simplifications, really truly simulate chemistry. And we could theoretically build a simulation of a world and let it run for millions of years and then solve all the problems to our society. So why do I bring this up now? Well, as you'll see, these molecules are not static. This molecule is sort of locked like a snapshot, like a photograph, but in fact, all of those circles can rotate. And we call these rotations conformations. So when the chemists designed this program that allowed the molecule to fit inside of this enzyme, they had to allow the molecule to adopt different rotations. The molecule may be rotated like this, or the individual bonds can twist around too to see that if it will actually fit inside of that enzyme. And so today we're going to learn about the rules that govern the rotations of bonds in molecules, and we call these rules conformational analysis. So let's take a look. Conformational analysis. So the main principle behind this theory is that molecules move. They are not static. And there are a number of movements that are possible for molecules. They can undergo something called translation. Translation is a fancy word that just means that the molecule is sort of scooting around in X, Y, or Z direction. So, you know, if you just take a glass of water and pick it up, that's translation. There's also vibration. So the glass of water could shake. So just like that, a molecule could shake. So vibration is another type of movement that can that a molecule can undergo. And then also there is rotation. So the molecule can rotate. along an axis. And that's really what we want to talk about today, is rotation. That is the key for conformational analysis. So let's just do a quick review from our first lesson, and that is to draw the bonding of ethane. And I think back in the beginning of this class we looked at methane, but ethane is very similar, it just has one extra carbon. So the perspective drawing of ethane looks like this. There's 2 carbons, and then we have some hydrogens coming off of those carbons. It looks like this. Okay, there's the perspective drawing of ethane. And now I'm going to redraw this using the orbitals, you know, the sp3 orbitals and stuff. So we have carbon, carbon, hydrogen, 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 hydrogen. And I'm just going to draw the little 1s orbitals for the hydrogens. Okay. And then in blue, I'm going to have the sp3 orbitals drawn. So these are the sp3 orbitals. We have sp3 orbitals bonding to the hydrogens as well. We talked about why carbon is sp3 hybridized in methane and ethane. So it's having to attach to 4 different atoms. And I want to focus right here on the center. Between the 2 carbons, there are 2 sp3 orbitals. And these sp3 orbitals create a sigma bond. And the take-home message for this slide is not, you know, you're not going to have to draw pictures like that. It is just to know that sigma bonds can freely rotate. So it's not locked in place, but rather the carbons are twisting around, and they can spin around actually quite fast. It all depends on the temperature. Obviously, if you heat the molecule up, the carbons are going to start spinning a lot faster, because temperature is a form of thermal energy, which talks a lot about the rotation of the individual bonds. So this is a sigma bond, and it can freely rotate. And so why do we care about this? What does it matter if the carbons rotate? Well, look what happens when the carbons rotate. The hydrogens on the outside also rotate because they're attached to the carbons. So you've got like this little propeller thing going on. This is very rich. This is robust. This is interesting. This creates some interesting consequences on a 3D level. So as sigma bonds rotate, the 3D shape of the molecule changes. And we know that's important when it comes to, say, fitting inside of an enzyme and curing cancer. And I'm not exaggerating at all about that. That's 100% true. So the 3D shape of the molecule changes and the energy changes. It turns out that there are some restrictions of the rotation. So like as you rotate it, sometimes things can start bumping into each other. If there's like a lot of bulky groups on the carbons, there can be some rotations that are more low in energy than others. So different rotational states have a name called conformations. So that's the name, conformations. So let's take a look at how we can represent these different rotations with a much clearer picture called a Newman projection, and also how we can calculate the energies of these different rotations. I'll admit it, this is kind of boring. I mean, who really cares about the energies of different rotations of molecules? It's so like, you know, overly detailed, but it's actually pretty important, and we are going to see some problems on our midterm that require us to calculate the energies of these rotations. So let's take a look. So, oops, my thing crashed there. I did not like that. It was, let me find my, sometimes my note-taking app just crashes because it's just too much for it to handle. My notes are just too amazing. Let's take a look again at ethane, and we're going to talk about, like I said, these Newman projections. So I'm just going to draw kind of a simple picture of ethane here. I'm not going to worry about too much of the bonds being wedges or dashes or any of that perspective drawing nonsense. Just a simple version of ethane. And I'm going to go ahead and draw a blue arrow over this carbon here and a red arrow over this carbon here, and you'll see why in a moment. So what we'd like to do for the Newman projection is to put our creepy little eyeball, this is our creepy little disembodied eyeball, to show that we're going to look down the carbon from the side. So instead of looking at straight on, we're going to turn our head and look at it from the side. And so that's what this little eyeball represents. Okay, so now let me show you how to draw the Newman projection. We start by just drawing a dot, and this dot is going to represent our front carbon. And then what's attached to that front carbon is our rear carbon, which will indicate with a big circle. Okay, so our front carbon is just this dot, and this big circle around it is the rear carbon. So attached to our front carbon, what do we have? We have 3 hydrogens attached. So I'm just going to draw in those hydrogens. So see how we have 3 hydrogens attached to the front carbon? Now to the rear carbon, we're also going to have 3 hydrogens attached. Now obviously the carbons are both the same size, but we're making the front carbon really, really small so that we can see the rear carbon behind it a little bit clearer. So this is an exaggerated drawing. So just to recap, this little front dot represents the front carbon, which we indicated with the blue arrow. And the rear carbon is represented by this large circle, and we indicated that with red. And so you can see this is one possible rotation that this molecule could exhibit. This is one type of conformation. And if you were to calculate the angles between these hydrogens, the front hydrogen and the back hydrogen, you would see it's 60 degrees. Now it turns out that this conformation is really favored. It's called staggered. And the reason this is favorable is that it's sort of creating the maximum distance between the hydrogens in the front carbon and the hydrogens on the back carbon. And you can imagine when atoms get close to each other, they start to get stressed out because their electrons are inside of the bonds and they start repelling each other. And so you end up with a situation where hydrogens, they don't want to be close to each other. They want to be as far away from each other as possible. And the staggered conformation allows that. So now let's take a look at the eclipsed conformation. So this is versus. So what I'm actually going to do is I'm going to leave the front carbon totally still. So I'm just going to leave the front carbon the way it was. So it's got 3 hydrogens attached. And what I'm going to do is I'm going to turn the rear carbon. I'm going to rotate the rear carbon so that it's in a different conformation. So the rear carbon is going to turn a little bit. And so when the rear carbon turns, the hydrogens on it are going to move clockwise if I'm going to rotate it clockwise, okay? So when I do that now, this hydrogen, which was pointing straight up, is going to move to the right, and now it's sort of closer to the front hydrogen. Okay, and I'm going to do the same thing with the other hydrogens. So that one's also going to move, and I'm trying to make it so they're perfectly overlapping, but obviously that's not possible because you won't be able to see that, right? But can you tell that the hydrogens in the back have sort of rotated to overlap with the hydrogens in the front? That's what I'm trying to represent, such that the angle between these hydrogens is now 0 degrees, meaning they're right on top of each other. Now this is called the eclipsed conformation. It's like the solar eclipse, where the sun and the moon are all lined up. I don't know what type of eclipse that is or whatever. But where you've got these atoms lined up on top of each other, we call that eclipsed. So which one of these do you think is higher in energy? Eclipsed, absolutely. Because now we have overlapping hydrogens, which is, of course, not favored. So we can say the following: eclipsed is higher in energy than staggered by, and this has actually been calculated, 3.0 kilocalories per mole. So not a huge difference in energy, but still significant, 3 kilocalories per mole. And the reason for that is that each HH eclipse costs 1.0 kcals per mole. And you can see in the eclipse form there are 3 hydrogens eclipsing, so that's why 1 plus 1 plus 1 equals 3. Okay, so this is a pretty simple analysis for ethane, but let's amp up the difficulty and take a look at butane. So let's try butane. Okay, and for butane, it has the following structure. We've got 4 carbons, all in a line, and of course we do have some hydrogens on those central carbons. All right, so there's butane. You can see 1, 2, 3, 4 carbons, or we could represent the butane using some abbreviations. So do you remember the abbreviation for methyl group? That's right, it's Me. So we can, it's not really saving us much time, but I just want to get you all comfortable with the fact that I use abbreviations. And I'm going to replace the CH3 groups with Me abbreviations. All right, so now let's do a conformational analysis of butane. And so I'm going to get my creepy little disembodied eyeball to start looking down this bond to the side. And as we draw the following kind of conformations, I want you to keep in mind 4 different types of interactions. So let me just make a little table here and we'll go over these interactions as we go. So interaction, and then that'll be the first column, and then the second column will be the energy cost in kcals per mole. So the first interaction we've already seen is an HH eclipse, and that cost is 1.0 kcals per mole. We're going to see in butane there's another possible eclipse, H over methyl. H over methyl is 1.4 kcals per mole. It's even worse, that because the methyl is bigger than a hydrogen, so the overlapping of a hydrogen and methyl is worse than hydrogen and hydrogen, so the energy cost is greater. What if we had, ooh, this is a good one. What about methyl over methyl eclipse? This is really, really bad because the methyl groups are quite a bit larger than hydrogens. I mean, each methyl group has a carbon and 3 hydrogens, so you can imagine it's significantly larger than just a hydrogen. The energy cost of that is a whopping 3.1 kcals per mole. And there's one more interaction. This one's kind of weird, and we'll talk about what this is. Methyl-methyl gauche. G-A-U-C-H-E, gauche. What is gauche? We'll talk about what gauche is in a moment, but that has an energy cost of 0.9 kcals per mole. And those are the 4 interactions you need to know in this part of the class. That's it. These are the only 4 interactions you're ever going to see. There's a table with more interactions, you know, with chlorines and things like that, but we're just going to worry about these 4. Okay, let's start by drawing the worst possible conformation that we can for this molecule using our Newman projection. So let's go ahead and represent our front carbon and our back carbon. And so if we want to draw the worst possible conformation that we can, we should make it as eclipsed as possible. Okay, so let's take a look at what's on our front carbon here. Connected to our front carbon, we have a methyl, a hydrogen, and a hydrogen. So we can just go ahead and put that anywhere. So I'll put the methyl at the top, just randomly. And we have a hydrogen and a hydrogen. And now, connected to the rear carbon, what do we have? Connected to the rear carbon, we have a methyl, a hydrogen, and a hydrogen also. So let's see how we can rotate that rear carbon so that this is as bad as it can possibly be. And what we should do is put the 2 methyl groups eclipsing on each other. So I'm going to try and represent it so that the 2 methyl groups are right on top of each other. So there's the methyl group on the back carbon. Obviously, I can't draw it directly on top, but I'm trying to make it close. Then we have the hydrogen on the back carbon. and then we have the other hydrogen on the back carbon. Okay, so the methyls are lined up, the hydrogens are lined up. This is terrible. We call this conformation totally eclipsed. And it refers to the absolute worst case scenario. And so we can actually add up now all the energy of the interactions and figure out the total energy of this conformation. So the first interaction we have is a methyl-methyl eclipse. So Me eclipse. And if we look at our table, the energy cost of that is 3.1 kcals per mole. And then we have two HH eclipsing interactions. So 2 times HH eclipse. And that is going to be 2.0 because each one is worth 1 and we have 2 of them. So that'll be 2.0. So the total energy here is 5.1 kcals per mole. All right, and we'll just set this arbitrarily to 0 degrees. And now what we're going to do is we're going to keep the back carbon still, and we'll rotate the front carbon to explore all the different conformations. So let's try now the 60 degrees conformation. And so, like I said, we'll keep the back carbon totally the same. So for the back carbon, we have a methyl going up, hydrogen, hydrogen. And now we're going to rotate the front carbon 60 degrees to the right. So now it's going to look like this. The methyl group that was straight up is now going to move 60 degrees to the right. So now our methyl group is here, our H is here, and our H is here. Okay, this is another conformation, and this one we would call staggered because it's nice and staggered. And what interactions do we have? Well, we have this is our methyl-methyl gauche interaction. Methyl-methyl gauche is because the methyl groups are so big that even when they're staggered 60 degrees from one another, there's an energy cost associated with that. So these two methyl groups are gauche to each other because they're 60 degrees from each other. So this is methyl-methyl gauche. And so the total energy is 0.9 kcals per mole. These two hydrogens are also gauche, but there is no cost for a hydrogen-hydrogen gauche. And this hydrogen and this methyl are also gauche, but there is no cost for that either. It's just methyl and methyl that has a cost. Okay, let's rotate another 60 degrees. So this will take us to 120 degrees. Again, we'll keep our back carbon completely still. So the methyl will always be up for the back carbon. Hydrogens on the right and left. Okay, now we're going to move again our front carbon 60 degrees. So now it's going to be kind of over here, over here, and over here. Now the methyl is down here. Hydrogen, hydrogen. Okay, so now we're back to an eclipsed form. Not totally eclipsed because it's not the worst possible eclipse. We don't have the methyls right on top of each other. And let's see what interactions we have. We have a hydrogen methyl eclipse, another hydrogen methyl eclipse. So we have 2x HME eclipse. And so that's going to be a total energy of 1.4 times 2, which is 2.8. And then we also have a hydrogen-hydrogen eclipse, which we know is worth 1. So the total energy here is 3.8 kcals per mole. Sweet. Okay, let's do 180 degrees next. So we'll go down here and we'll do 180 degrees. Again, we'll keep our back carbon totally still. Methyl, H, H. Now our front carbon's moving another 60 degrees. So now the methyl is here. Okay, now this is actually the best form that we can draw. We call this one anti. And this one's really good because the two methyl groups are as far away from each other as possible. There's no gauche methyl-methyl interaction, and it's staggered. So it's the anti-staggered. There's none of our interactions here, so this energy is just 0.0. This is amazing. So what that means is that butane most of the time is going to want to be chilling like this because that's super low in energy. There's no bad interactions at all, no overlapping at all. But we're not going to stop there. Let's keep moving. Another 60 degrees will take us to 240 degrees. Again, we'll keep our back carbon totally still. And now our front carbon will move. Another 60 degrees. So now our methyl group is over on the left. And our hydrogens are the upper right and lower right. And it looks like, again, we have two methyl hydrogen eclipsing interactions and a hydrogen-hydrogen eclipse. So this one's similar to the one we did at 120 degrees. So this is eclipsed. And we have HME eclipse times 2. So that's going to be 2.8 kcals per mole for that, because it's 1.4 times 2. And then we also have a hydrogen-hydrogen eclipsing in the bottom right. That's going to be 1.0, so this gives us 3.8. And then finally, there's one more possibility. We're going 300 degrees before we're back to 360. Okay. Keep our back carbon the same. Back to staggered. Now the methyl's in the upper left for our front carbon. So this is staggered. You notice that for each 60 degrees, we alternate between being eclipsed, staggered, eclipsed, staggered. And this one here, what interaction does this have? It has a methyl-methyl gauche. And so the energy for that is 0.9. Sweet. Okay, so now we calculated the energies for every single conformation. So we did a full conformational analysis, and I'll have you do one of these on problem set 2. So if you want practice to do one on a slightly different molecule, you'll have the pleasure of doing that. And so now what we want to do is just cap off this amazing work we did. Why not make an energy plot to show our results? We can graph these results, and so that's kind of fun if you like to graph. So let's take a look at that at the next page. Let's create a little bit of a graph. So I'll put our y-axis and our x-axis. And for our y-axis, we'll call that energy. And for the x-axis, we will call that dihedral angle. This is the angle of rotation. Okay, so for our energy, let's get a couple lines going. We'll do 1, 2, 3, 4, 5. So 1 kcal per mole, 2 kcals per mole, 3, 4, and 5. And we'll set this equal to 0 degrees, and then we'll have 60, 120, 180, 240, 300, and then back to 360. So 60, 120, 180, 240, 300. Okay, those are all of our angles, and now let's just go ahead and plot. So at 0 degrees, we were at 5.1. So I'll put a dot there at 5.1 at 0 degrees. Then when we went to 60 degrees, we were at 0.9. Here's our 60 degrees. So we save a lot of energy to go to 0.9. At 120 degrees, we were at 3.8. It's right here. So we'll go like right here. At 180 degrees, remember that was the ante, where we had the lowest possible energy, and that was 0 degrees. So we'll just put I mean 0 energy at 180 degrees. And then at 240, we were back to 3.8. At 300, we were back to 0.9. And then at 360, we're back to where we started, so at 0, so we're back up to our 5.1. Okay, so there's all the lines, and now we can kind of try and connect them together. Let's see if I can do a nice smooth connection here. And so this would be the energy plot for butane. So we could call this the conformational energy plot for butane. Awesome. All right, so why don't we stop right there? I think this is a good stopping place because this has been kind of dense. So we will continue actually talking about conformations a little bit in the next lesson, where we're going to talk about the conformations of a special type of molecule that's very common in organic chemistry called the cyclohexane. So stay tuned for that, for a little bit more conversation about these conformations.